begin by I'm reminding you of the definition of a category, right? So a category, I'll write cat for category. A category has objects and it has morphisms. Objects are denoted by maybe dots or some other symbols or letters like that. And morphisms are denoted by arrows. And sometimes one says the category has arrows. Morphisms are denoted by arrows, and the arrows terminate and co-terminate in objects. So this is an object, and this is an object, and this arrow labeled F is a morphism. Now it looks like the notation for a function from a set A to a set B, but it isn't. It's just an arrow, and it's an arrow that is between two objects. So that's what a category is, what's given in a category. And then the axioms are, in some order that I don't know if it is standard, is that given an object A, there is a special morphism from the object to itself called the identity morphism, whose property I will tell you in a moment. Given a morphism from A to B and another morphism from B to C, there exists a new morphism which I shall call FG, which is not the way people normally write it, but it's easier for me, and I won't keep writing it wrong. This is called the composition of F and G. All right. Now, the people normally write that GF, as you probably know, but I'll write it FG because it's in the order in which my arrows go, and so locally we shouldn't have any complaints about that. All right. So so in other words, it says that if you have an arrow from A to B and you have an arrow from B to C, then there is an arrow from A to C. If you think of arrow as a way of getting from A to B, then of course there would be a way to get from A to C by doing F and then G. To the composition. And then you have that if you went from A to B, and then you went to B by its identity, then that will be exact, that composition will be the same as F. F is equal to F 1 sub, excuse me, that's 1 sub B. F is equal to 1 sub B. The identity acts like an identity. It doesn't change the composition.
Is it A to B and then you said B to B?
I said A to B and B to B. The identity goes from B to itself.
Okay.
And if you travel from B to itself, it didn't do anything.
I'm just a term identity.
It's an identity. And similarly on the other side. And on the other side. I write that. And then thirdly, I guess thirdly happens on the next page. Thirdly, if you have a morphism from A to B, and a morphism from B to C, and a morphism from C to D, then you have F, and you have G, and you have H. You see you have some choices here. You could compose F with G, and then you could compose that with H, forming FG and then H. Or you could have looked at B and C first and formed a GH, and then you could have formed F with that, and you could have formed F with GH. And the axiom is that these are equal, that the composition of morphisms is associative. I've now reached the end of the definition. That's a category. Category is something with arrows and objects, and composition of the arrows is associative, and there are identities. Okay, very abstract, but you know many examples of this. How many examples, you might reflect for a moment how many examples of categories you know from one experience or another. Right. For example, if you're a mathematician, then there are piles of them that you would think of, because you could take the category of topological spaces, for example, and maps between them are continuous maps between topological spaces. Continuous maps compose to give you continuous maps who have identities and so on. And then if you're just using sets, then there are categories. But then there are categories, where the maps are just maps of sets and so on. And then there are categories which have structure which are quite different from sets. For example, for a topologist, here's a nice example for a topologist of a category that is different from a very set theoretical kind of category. I consider braiding. Like that. Now, let's not use the language of categories just now, let's just talk about braiding. And so here's a braid. So how would I describe that if I'm thinking either physically or topologically? I have some strings, they start at a fixed set of points, they go on downward, always downward, never getting entangled with themselves, but they entangle with one another and end up at a certain set of points. The set of points that they end up at the bottom should be regarded as the same set of points that they started at the top. But point number 1 here ended up at point number 2. Point number 2 ended up at point number 3, and point number 3 ended up at point number 1. So there might be a permutation involved. And as far as braiding is concerned, I would regard this braid as being equivalent to, let me draw one that it's equivalent to by making some change. Let's say, I don't want to make a big change. Let's put a break there and put that there. All right. And then maybe I just put a little wiggle in there like that, so it changed like that, right? Those would be the same braid. I'm just deforming the strands a little bit. A more serious example would be this braid here, where I have this braid, and this braid is equivalent to this one. So what I'm allowed to do to a braid is deform its individual strands. They must not touch one another, but each strand is seen as moving around, and they're moving around in such a way that they still always go down. They don't touch one another, and they move around and can deform. So in this case, this braid ends up unwinding and turning into that braid, and so that's what braids are. And you can multiply two braids and form a new one by attaching them top to bottom. So if I have a braid here, I'm just going to use 3 strands, but it could have n strands, right? If I have another one, then I compose them like this to get a new one by attaching the strands to one another. So for example, if I take this braid here and this one here, then I multiply them by attaching their corresponding point strands to one another, and I get a new braid like that. So if this braid was F and this braid was G, then this braid is FG. All right? Well, you see I have a category, but what are my objects and what are my morphisms? Well, the morphisms are the braids themselves, right? So the arrow has more structure. The arrow is all the structure of the braid, and it isn't a map of one set to another. It is the braid itself. The morphism is quite robust here. The objects are very desiccated. What are the objects? The objects are just, for the 3-strand braids, the objects are just these 3 points, right? That's all. That's the object. and you go from 3 strands to 3 strands to 3 strands to 3 strands. So if it's 3-stranded braids, there's only one object in the category, and piles of morphisms, right? All sorts of complex topological morphisms. So, it's when you see something like that that you might change your mind and think that categories are an interesting subject. If you're a topologist, I don't know what changes your mind. If you're a computer scientist or someone else, there are lots of other motivations, but I'm talking about topological motivations for categories here.
And is that your own motivation for studying braids? Or what is the primary motivation?
Oh, why do I study braids?
Yes. Yeah.
There are probably people who study braids because they are a very interesting category.
Yeah.
There are category theorists who went deeply into braids, like Joao and Street a long time ago, and they surely were interested in braids because they had certain very interesting properties in terms of categories. But topologists, well, the first person who studied braids was Emil Artin, and he was an algebraist, and I think he just thought it was a really interesting idea to follow up. Then topologists themselves study braids. Let me see. I was just trying to think historically. I think Emil Artin made up the subject of braids after J.W. Alexander in the 1920s proved a very good theorem about knots and braids.
Right.
And J.W. Alexander proved that any knot can be put into the form of a closed braid. All right? So what that means is, let me conserve paper and draw one up here. Let me see. 1 to 3. 1, 2, 3. I put one more there. And this is a braid. And then this nice topological operation that people like to do on braids is called a closure, right? And you take and you make it into something which goes around circularly like that, right? So now it's circulating around an axis like that. So now it's a knot. If I've made, let me see, did I make a knot? Yeah, I did, right? So there's a knot going around an axis, right? And Alexander proved that any knot whatsoever can be put into the form of a braid running around an axis. And this is why topologists who are thinking about knots got interested in braids.
Yeah.
Because every knot can be represented as a braid, and a braid has a nice algebraic structure or a category structure, if you like. And so that suggests that maybe we could understand knots by understanding braids, and that is one way to attempt to do that.
Can the algebra of real numbers be considered a category?
I'm sorry?
Can the algebra of real numbers be considered a
Can
category?
algebra?
Can the algebra of real numbers be considered a category?
Oh, yeah.
Okay.
But there, you have to decide what composition you're interested in, don't you? Because as I said, a category has one composition. Now, of course, there might be other compositions related to it, but there's a primary composition in a category, and so I could say that it would be addition. Or it might be multiplication, or maybe it would be some other strange thing. Yeah, but someone else was saying something.
I was kind of inclined to ask a supplementary question to the one I just asked. And has there ever been any conscious idea of trying to apply this concept outside of the study of knots and so on to anything else?
Yes, indeed. Braids are of interest to lots of people. The first mathematical thing you can point out about a braid is that it does have an underlying permutation, right? Just like this braid, if I label the points here and the points here, then underneath the structure of the braid, we have the permutation 1 to 2, 2 to 1, and 3 to 2, right? If I made a mistake, 3 to 1. So, well, anyway, that permutation. And so there's a mapping from braids to permutations. But what does that mean? That means that permutations, which of course are ubiquitous and are studied for all sorts of reasons, physics and algebra and everything, there is this natural algebraic structure called the braid group, which lies right next to the permutation group. And so algebraists so often are using braid groups because of that. And then for physics, if you have two-dimensional physics, then you can have a change of phase as one particle goes around the other, at least in principle. In three-dimensional physics, if you have one particle going around another, then there's a deformation of the loop all the way back to not really going around it at all. And so you don't expect to get a phase change as you move one particle around another in three space, unless that particle was not a particle, but was maybe an entire field line, or you were in two-dimensional physics. So if you have something like one particle going around a field line, or two particles going around one another in a planar physical situation, then you can have non-trivial phase changes. And those non-trivial phase changes correspond to braiding. Right. And the braid is a world line. I mean, you could think of it that way. You could think that the categorical direction that we have decided on for braids corresponds to time, and the morphisms are world lines. Right. Then again, the objects are very simple, but the world lines are very complicated. And so braiding comes up in a lot of physics because of that.
Okay, that puts it nicely in context.
Yes. So braids are interesting. Now, in the case of braids, the objects are just sets of points. So I could say braids, and I haven't said whether it's one strand, two strands, three strands, or four. And then the objects are all sets of points. No points, or well, it could be 1 point, 2 points, 3 points, 4 points, and so on. But endpoints go to endpoints. And so it all breaks up into individual pieces that way. So that's a nice topological category. As I said, I'm just chatting about topological categories and topology. So let me show you another one that's closely related to braids, and this I'm going to call the temporally lead category. Somebody is asking me about that. Sorry.
It's not a question. Or at least it's... I thought that your train of argument was, we have seen so far a composition between braids. What happens if I take into account the third action, which is taking arrows instead of objects in consideration?
The braid is an arrow.
I see.
They always go down.
Arrow can be reinterpreted. I mean, you can say whatever it is the arrow. The braid is the arrow, right? Do braids satisfy the axioms,
okay,
right? Well, do they? Let's just think, right? We know how to take two braids and multiply them, so that's the composition. What's the identity? Let me go back, and I'm trying to keep from using up all the paper. What is the identity for the three-strand braids? Well, you see what it is. It is exactly this, right? There is a braid, our simplest possible braid. No weaving going on, and if you multiply by that braid, you don't do anything. So there's an identity. And then associativity. Well, I let you draw some pictures for yourself to convince yourself that indeed braid multiplication is associative. That's because you can slide things around a bit, as long as you are allowed to slide things around topologically, then it's okay. It really is associative. And what more did we need? Associative, identity, composition, words, that's all we need. Definition of category is very simple. Yeah.
Could you view us the link to the stuff to this HOTT thing we hear about?
I'm sorry?
Homotopy type theory we hear about these days.
Homotopy type theory.
Can you link it up? a bit?
Yeah, so I can only say something very tiny about homotopy type theory. The idea, as I understand it, is that you're looking for a good concept for what it would mean for two things to be of the same type. All right? So so in homotopy type theory, there is an abstraction of the notion of path. And if you had a notion of path, then you say that two things are of the same type if there's a path from one to the other. All right? So for example, if there is a path, so let me do an example or two, a topological example. Let's not use that one. First I give you a topological example. Here's a point, and here is a disk. And here's a slightly smaller disk, and here's a slightly smaller disk, and yet a smaller disk, and yet a smaller disk, and yet a smaller disk. This is a disk of radius 1, this is a disk of radius 1/2, this is a disk of radius 1/3, this is a disk of radius 1/4, 5th, 6th, and so on, and we get a continuous range of disks all the way down to a point. So there's a pathway in the space, in topological spaces, disks and points, a continuous pathway which starts at a disk and ends up at a point. And so one says in topology, one says that the point P has the homotopy type of a disk. The disk and a point have the same homotopy type. Right? So there's a whole field of topology that deals in homotopy types, where it's not homeomorphisms of spaces, but you can deform the spaces and sort of get the core space out of a given space. So, for example, just to give you another example, consider an annulus. And sitting down in the middle of the annulus is a core circle. So here's this circle. So here I have annulus, and here I have circle. I can't spell, but anyway. They have the same homotopy type. And the reason is that you can contract the band until it just left with. So in homotopy type theory, not homotopy category type theory, but just ordinary homotopy type theory that topologists are interested in, they're kind of looking for the core structure of a space, and so they allow themselves to deform the spaces. And the basic notion is that there should be a path from one thing to another, a continuous path from one thing to another that corresponds to having the same type. So the people who brought you homotopy type theory, categorical homotopy type theory, abstracted the notion of path and starting the base with the notion of type as homotopy, as something like homotopy type, that there should be something like a path. Now it could be a discrete path instead of a continuous path. Then how that speaks to various questions you might have in your mind about type theory, I probably can't answer, because I don't know the theory well enough.
People seem to be speaking with considerable value for this system at the moment, I think, and they've
Yeah, that's correct, they do.
It's a bit hard for me to see where that comes out of, that's all.
Right. So I'm not giving a lecture on homotopy type theory, and I haven't learned enough of it to explain to you why people take so much value in that theory. There may be other people here who could talk about that. Maybe Mike could tell us more about that. Right? All right. So where was I? I am going to talk about paths in another way in a moment, but I wanted to give you this example, and then we should watch the time. Yeah, okay. So here's another elementary category, like the braid category, that's interesting to understand. This time, I have a set of points, maybe 3, and I'm allowed to connect them up to one another like I do with a braid, but I have to draw it in the plane, and I am allowed to draw back to a point that I already had. So this would be an example of a morphism in the temporally lead category. A morphism in the temporally lead category is a connection structure between a set of points and another set of points. Connection structure means this point is connected to that one, this one is connected to that one, and this one is connected to that one. All right? That's all. And I give you another example of a morphism so you see what I mean. Let me see. Yeah. Sorry. Let's have 4 points up there. Well, all right, that's another example, but I'm looking for a different example. What's my other example? There. I'm trying not to draw complicated examples for a simple idea. Here I have 3 points at the bottom and 1 at the top. And I've fulfilled the condition. The condition is that points should be connected to other points. No point is left unconnected with somebody. But now the morphism goes from 3 to 1. So now I have a category in which, as you see, I can have objects are points, 1, 2, 3, 4. Morphisms are between points, but I don't have to have the same number of points down here as up there. Okay? And this category has lots of structure in it, just as the braids do, and turns out to be useful in statistical mechanics and other situations. And just to show you a bit of combinatorics that can happen with this, let's look at this guy here. Oh, that one. That one will do. Let's call this alpha. Let's look at the square of alpha. Let's look at alpha composed with alpha. So here's alpha, and here's alpha again. All right. And I'm going to compose them, which means that I connect up the bottom points to the top points. Right? Like that. There's my composition. But remember, I'm doing this topologically. All I care about is the fact that this is connected to this. I can straighten it out. So this is the same as straightening it out. But once I straighten it out, I get alpha back. So I have alpha squared is equal to alpha. I get an idempotent element. I get a projector. And so these algebras are related to idempotence. They're related to von Neumann algebras, and they're related to physics and various things. And nice diagrams, and the diagrams are the morphisms in the category.
So yet another obvious category would be a binary tree or a trinary tree, or
I'm sorry?
Yet another category would be a binary tree, or
a binary tree is a nice object, right? So here's some binary tree, a finite one, right? Now, there are various ways to make trees into categories, but the tree itself is not a category. The tree is a tree.
Okay.
But if you have some favorite way of composing trees to get new trees, then you're going to have a category.
Okay.
Right? So it might be that you have 2 trees and you're going to put them together in some way to make a new tree. What's one way to do that? Well, if they have roots, like this tree has a root, sorry, the root is up in the sky, but that, well, it has a natural root. I have another tree with a root, then I can put them together and put a root on that, and I have a way of composing trees, and then I will have a category that's related.
And the same applies to any order of trees.
Yeah, so there are many, it gives you a way of you have situations where there are compositions, and you aren't really constrained too much other than that you would like to have these compositions or you want to think about them, then categories are right there in front of you. Relationships give rise to, such relationships give rise to compositions, and compositions give rise to categories. So they come out of very elementary situations very often, just as sex apparently do to those of us who are so thoroughly indoctrinated in that. They're really it's a very elementary idea.
Suppose you have a partial order or a lattice.
Yeah.
What happens in that case?
Well, in a lattice you often have composition of one kind or another. It might be meet or join, right, in the lattice. And then once you have compositions, you can make categories. And then you have more than one category, as I was saying about real numbers. It depends on what compositions are in your mind to put forward.
Thank you.
Right. Yeah.
If the 1 to 3 brain, let's call it beta, what would beta squared look like?
I'm sorry.
The 1 to 3 brain.
1, 2, 3. No,
This one, the 1.
Yeah, the 1 to 3. Right.
Let's
By the
call
way,
it 1 beta.
or 3 to 1.
Or 3 to 1.
I'm going down the page.
Yeah.
Am I going to go down the page? Then it's 1 to 3.
Yeah. Okay. Let's call it beta. What would beta squared look like?
Oh, what does that square look
Yes.
like? Well, good question, and something else is happening.
Actually,
here.
that's what I was going to ask
If
you.
I take this guy and I square him, then I would get, oh, I'm sorry. No, I can't square him because he doesn't have a codomain that matches the domain, right?
Right.
This goes 1 to 3, and I have to have a 3 coming out, right?
Okay.
But of course I could do, but the one I had in mind when you asked me the question was composing this one with, let's say, this one, just for writing it down, right? So this is 1 to 3 and this is 3 to 1. I could compose those. What will happen if I do? Then I will get this. And that's something that happens here that's important. You get a loop, I'll tell you.
Okay.
Right? Now the loop could be regarded as a special morphism from 0 to 0, if you want to. But I'll just regard it as a loop, and it's an extra entity, and I'll pull it out like an algebra entity and pull it out. Until we end up with 1 to 1 here.
Okay, so you basically this multiplication,
Yeah.
like matrices that will match.
Yeah.
Okay, thank you.
Now taking the topological categorical point of view on these things, you could ask the question, well, how did it happen that alpha squared was equal to alpha? You saw it happen because this topological wiggle went away, right? But if you look at the structure of alpha, let's do it on another board. This is a good board. So here was alpha. And alpha is actually equal to a composition in the category, isn't it? It's a composition of one of those things that we were just talking about. I'll put a little dotted line to show you where it's composed. And another one here. So alpha is equal to A times B. A composed with B. Where now we're going from 3 to 1 and then from 1 to 3. I'm really working in the category. I'm not in an algebra anymore. But there's a composition in the category of those two. All right. Now, what happens, just like your question, what happens if I form BA? Well, then I get this, and I get this, and that's the wiggle, right? So we have that B times A is actually equal to an identity. It goes from 1 to 1, and it's just the identity on 1 in this category. And that's really what made alpha squared equal to the identity. The story can be told algebraically now. Alpha is AB, and alpha squared is AB, and now because of associativity, I look in the middle there and see, that's just the identity, and so I get AB back, which is just alpha, and so alpha squared is equal to the identity. Alpha squared is equal to alpha because of the fact that the middle guys were equal to the identity. Well, why am I belaboring this? Because when you went up to the category and you looked at this puzzle, how do I make things whose square is equal? How do I make idempotents? How do I make them? In the category, the story is made clear. I need to create things which multiply to give me the identity. So for example, I draw this, which is the identity, because topologically there are a lot of identities, and then I factor it, and I call this one a B and this one A. So then I have this guy here, and this fellow over here. This is B, and this is A. And now if I put them in the opposite order, A, and then B, this went all the way over to the left, so it continues here when I form AB. Sorry, I did that without any intermediate work, but here's B and here's A, and there's only one. They have the one. So you see, it starts from 1 and it goes to 5, and here's 5 going to 1. But with the one parts have to be identified with one another. Sorry, that was meant for emphasis, but it will confuse you. So I form AB. AB squared will be equal to the identity.
No.
Because when you multiply it by itself, it will have the BA in the middle, and that part undoes itself and goes away, and AB is reproduced all over again.
Lou, can I ask in my sort of cursory reading of category theory, I come across these things called pullbacks and push-outs.
That's another story.
Okay, I was just wondering what does that mean?
Well, all I'm doing is playing with a topological category, and I haven't introduced anything like that yet.
Okay,
right? So, I'm willing to say a word, but notice what I'm talking about is how topology and category interrelate to one another, right?
Okay.
And how a puzzle that you might have, how do these idempotents occur in a certain algebraic situation? If you look at it as a category, then you see that the idempotent involved it actually factors into two things in the category. It didn't factor in the algebra, factored in the category. And then you can see topologically what happens into these morphisms in that category, and you solve the problem of, there are now, you see there are infinitely many idempotents, all sorts of idempotents, corresponding to what people call meanders, a meander being something like this that goes like that, and you decided to cut it in the middle somewhere and factor it that way.
Can I ask another question? I'll ask another question then, because the other thing that really strikes me looking at you do this is the symmetry of the pictures.
Yeah.
The symmetry is a really key thing here, isn't it?
Well, but there's some asymmetry, right, because of the meander. The meander can do a lot of crazy stuff.
The if I forgive,
but the symmetry was AB versus BA. BA is the identity, but AB is complicated.
Yeah, the point perhaps to underline here, Lou, is that in order to compose, maps have got to have well-defined domains and codomains. Or perhaps more familiar to people in this room are the notions of source and target.
So you start with the identity
That's
from
the
1 to
point.
1.
Yes.
You mess it up in the middle, but you have, when you cut it, you have a certain...
You've got to keep control over the domains and codomains in order to have a well-defined notion of composition of maps.
Well, it's an example. Pullbacks and so on are generalizations of things that you were familiar with in set theory, like a product, or well,
relationships.
yeah, I mean,
I'll be talking
I
about
think I
those
don't,
later.
I'm just reluctant to go doing those.
No, don't worry,
constructions.
it's fine, I understand. Yeah.
Okay.
But, yeah.
One comment, to me, that looks completely like Wheeler's one electron universe.
I'm sorry.
This looks so much like Wheeler's one electron universe.
No, I missed a word, I'm sorry.
Wheeler's one electron universe.
A one electron universe.
Yeah. So you look at that, and if that's a word line,
Oh.
T is vertical.
Oh, that's what that reminded you of. Yeah, okay, right.
So
Everybody heard Garnett's remark, right? In the one electron universe where this is time, this electron is going forward and backward in time, and at this particular time slice, we have a universe with quite a large number of electrons, all the same.
And one less positive.
Except some of them are positrons and some of them are electrons.
Yeah, one more electron than positive.
But, what am
I created some Baronian rings for later, so
Okay.
they're coming out now
All right.
and will be replaced.
So now, I want to talk about something else, another kind of relationship with topology that's a bit more general. Suppose you have a category, and you consider some sequence of morphisms, like that. So there's a morphism, another morphism, another one. Maybe it starts in A and it goes to B and C and D and E, something like that. Well, there's lots and lots of that structure in any category that you happen to look at. Right? What was realized early on in category theory, but it's funny that this, what I'm about to show you, is well known to those who know it, and maybe somebody who's first learning about simplices, which is what I'm going to tell you about, never sees this until later, and maybe somebody who's learning about categories doesn't see it until a little later. But let me point out, I just want to point out that you have this, and it could mean lots of different things to you depending on what you're doing with the category. For example, it could be a process that you're modeling, and the process has transformations, so the sequences of these transformations correspond to the process. Or it might be paths in a graph that you're thinking about, or paths in the graph of the category. So sequences of morphisms that compose are important to think about. And then an object that topologists always learn about and geometers always learn about are simplices. So that's one simplex, a zero simplex, or a one simplex, a two simplex. Three simplex. And so on. Simplices. So certainly everybody who studies topology learns about simplices, and probably everybody who studies geometry learns about n-dimensional geometry, learns about n-dimensional simplices. But the interesting thing is that this guy is a simplex. And why? Let's look. Let's take a single one where you can't dispute it. That's certainly a one simplex. You wouldn't dispute it at all, right? There it is, it's a one simplex. But what about composing two of them? Well, we go back to the definition of category. This is at the basis. I'm going to stop putting elements in unless I need them. Here's FG. Well, that's a two simplex. Okay? So, given that I'm in a category where I know how to compose, then two arrows that compose with one another give me a two simplex. And what happens if I have three things that are composing? See if we can make the picture come out nicely. F, G, and H. Well, these can compose. Give me an FG. And these can compose, I'll try to draw them in back, and they give me a GH. And this can compose, and it gives me an FGH. But that's also the same as FGH, right? And that's in there too, somewhere. FGH is here, that back face. So what I drew for you, let me draw it again, is an ordinary simplex, and everything is compatible. So I won't draw everything on it, but maybe I could draw without arrows. Here's F and here's G, and here's H, and this was GH, and this was FG. And this could have been regarded as FGH, but it could also be regarded as the edge corresponding, that's in the back, or could be corresponding to the face in the front, which is FGH. And since we're in a category, you see that that fits together and gives me the unique morphism there, and it's a simplex. So, if I have 3 morphisms, then I get a simplex, and if I have 4, then I'll get the next higher dimensional simplex, and so on up the line. So the compositions of morphisms are simplices, and that means that if I have a category in front of me, then I have a big space made out of simplices all glued together, where each of the simplices is coming about in this way, and they're glued together, as you see how they're glued together. So every category corresponds to a big topological space of some high dimension, perhaps. Maybe infinitely dimensional. For example, suppose I had a category with one object and one non-trivial morphism that goes from the object to itself, right? Then I would have F, 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 so on, right? And so there are infinitely many simplices. It's like huge. And if I had a more finite category, like that category, if that was just the category, then there would just be the one simplex, and that's all there would be, right? So it depends on whether there are morphisms that come on back to where they started that are non-trivial, whether you would go off to infinity or not. But it means that a category corresponds to a space. So that's good for a topologist in the general sense. Maybe you could measure that space in one way or another, as topologists do, and try to understand the category in terms of the space. So that's an important idea, and this is called the nerve of a category, and it is used. And I'm not quite sure the history of this, but I think that the ideas must have arisen together for Eilenberg and Steenrod. I don't know. Maybe somebody who studied category literature can say to me, can tell us, at what point did people actually articulate the nerve of a category?
It is, I think, in Eilenberg and Steenrod.
I'm sorry?
It's in Eilenberg and Steenrod, I think.
That's what I would have thought.
52, yeah.
Okay.
It's not actually named as a nerve.
Right. Now, now I'm going to keep from getting technical, particularly since I have 5 minutes, or 10 minutes, but you know that if you have a space, you can compute its homology or its cohomology, and that can be computed directly in terms of the simplices in the space, because what you look at are the boundaries of things, and simplices have articulated boundaries, like the boundary of the simplex is this one plus this one minus that one, to go around. And so you can ask for those things that have zero boundary, the holes in the space, modulo those things that are boundaries, and that's called homology. And so you can look at the homology of a category. And you may keep track if the objects have internal structure, you may keep track of the internal structure of them at the same time in one way or another. But the basic idea is that a category is a space, and you can measure it with algebraic topological tools. So that's the large idea. The thing I wanted to show you was a remarkable idea and we have about 5 minutes.
No, I just thought it was the last sheet I was going to.
Oh, you're worried that there might be another. Oh, we have one more sheet.
And sorry, Luke, can I interject something very, very quickly indeed? And then, of course, it becomes very natural to see sets, which, of course, we were inculcated into thinking of as the starting point of everything. just as the case of totally disconnected spaces.
Yes, right, right.
So you can stand things on their head and see the content of the basic notions of set theory from a geometrical viewpoint.
All right, so what's your point is that if we start from set theory, this idea of set theory is totally disconnected things,
Yeah.
but then mappings between them
That's
that start building connections.
But starting from spaces, you can then come back to sets as the totally disconnected case,
Yeah, that's right, that's right.
which is special from the point of view of
Right.
spaces in general.
Right, and it's curious in its way that when you start with categories, whatever category it is, it's actually kind of a space.
Exactly, yeah.
So,
that was
so it's not
kind of conceptual
surprising
payoff of what
when you think that the idea of category was abstracted and invented by people who were doing topology.
Exactly.
Anyway.
Yeah.
And then that same movement of ideas is happening with the homotopy type theory, where someone is taking an idea from topology. But now I wanted to show you something that I'm intrigued by and have been thinking about for quite a while. Which starts with knot theory. So here's a knot, and there's a multiple viewpoint about a knot that is related to statistical mechanics. That maybe I've talked about before here, and it has to do with the following idea, combinatorial idea, that you would take each crossing in the knot and you would see that there was a binary, you would operate with a binary choice on that crossing. You could remove it by connecting the two lines this way, or you could move it by connecting the two arcs the other way. Two choices, like two states in an Ising model, but actually the relationship with statistical mechanics is more like this. Imagine that I did that to this knot in one of the possible ways. So I got this one, right? Now, what I'm looking at here are some curves in the plane. If I do this at every crossing, I smooth it out one way or the other at every crossing. I could get something like this, but I could also get something like that, right? Where at this crossing I smoothed it a different way, I left these two alone. So these are two different states. What kind of states are they? Well, if you think of this as something like a little statistical mechanics model, then what you're looking at are loops in that model that surround regions of constant spin. So that's actually a correct description, and I don't want to go into the details of it, but if you had a planar statistical mechanics model, it's usually based on some graph, and then there are regions for a given state of the model. There will be regions in the graph where within a given region you have constant spins in the model, right? And then the partition function for the model is the sum over all of the different spin configurations. So you can write it as a sum over all the different loops, where each loop configuration corresponds to a whole sum of things that have constant spins in that pattern. So, by analogy, by analogy, but actually it's directly connected to some statistical mechanics models, you can look at all of these loop states for a given knot. And then it turns out that you can get very interesting and non-trivial knot invariants by summing over all these different viewpoints on the knot, evaluating each one in an appropriate way. And that gives rise to models for things like the Jones polynomial. But you can also do the following, and this was an idea of Mikhail Kauffman quite a while ago by now. Let's look at all the states for this Huffling, which is easier to do. It's harder to draw all 8 of the ones for the Trefort knot, but we won't have any trouble with the Huffling. So here are these two states, all right? And then I call these A's. I might as well tell you my convention. When I smooth it this way, I call it an A. And when I smooth it the other way, I call it a B. The A and the B are discriminated from one another by, if you take the overcrossing line and turn it counterclockwise, it sweeps the A. All right? So you can discriminate A and B. And then, for example, this was 3 A's, and 3 A's, and this was a B and 2 A's. And every one of these is a code for the original knot diagram once you know the A's and the B's. So then what we're going to do is we're going to first draw the one with all the A's, and then we'll draw an arrow for every time we turn it into something with a B. So I get an arrow here, oops, that's a B, and I get a different arrow here, like that. That's a B, and this is an A. And then I get arrows here, which go like that, and two B's. So you see I get a graph like that with arrows in it. And Kauffman said, well, I'll take that to be a category. Where the objects are these funny combinatorial things, these loop states, and the arrows are just arrows. They just go from one to another. If there is a smoothing that takes one of these to one of these by one smoothing. And I have a category. So according to corresponding to the knot, I have Kauffman's category. It becomes a category how? These are the morphisms, except I didn't tell you about identities. So I put one identity morphism on each object, have a category. There's a category associated with the knot. All right.
So
What are you going to do with it?
What was the identity you were saying?
What?
What is your identity?
Oh,
Your identity morphism?
I just make one up.
Oh, all right.
Right? I say, all right, there'll be one more arrow, and it doesn't do anything.
Okay, all right, okay.
You know, I mean, you can always do that. If I want to make this coffee cup with the coffee in it into a category, all I do is I add an identity arrow.
Yeah.
It just has to have a self. And
Right, okay. Very nice, yeah.
yeah. So corresponding to every knot diagram, there's a category. Now, if you change the knot diagram a little bit, you get an equivalent knot diagram, but you get a different category, right? So now you have a problem. Kauffman immediately gave his answer, so that maybe I don't want to give you his answer because we're almost out of time anyway, but you see the problem. I want to know how to relate these categories to one another when I do a topological deformation of the knot. The category, well, I mean, this has 8 fins in it, right? If I had a knot with 40 crossings, there would be 2 to the 40th objects in its category, right? Big things are coming. And then many morphisms. So the nerve of the category, that space associated with the category, is going to be very high dimensional. But that's what he actually did was he figured out how to look at the nerve of the category in the right way and calculate some topological information about it and could get new invariants of knots. So you associate to the knot a category, and then you look at the topology of the category in the right way. You can get new invariants of knots. And of course it gets a little technical to go into that in detail, but we're out of time, luckily, so I don't have to tell you anything about it. But the thing is, it leads to lots of questions, particularly if you think about it in this abstract way. The usual notion of homology of a category by way of a nerve is virtually what he did, but he didn't do it that way. He did it in a way that looks like a subdivision of that or something, so that I've been trying to explore what the direct definition by way of the nerve will do, and other things, and homotopy related to it, and other things. It's very interesting to think about that. But then, for physics, it's also very interesting to think about it, because these things are the loop states for some statistical mechanics model, and you can look at this as taking the partition function and turning it into a category instead. Instead of summing over all the different possibilities, you make a category out of them and try to understand the global structure of that category. So I want to say it in as general a way as I can, and then maybe we'll have some moral about it later on. In quantum theory, you generally take all the possibilities and you have some way of evaluating each one, and you sum over them to form a wave function or analog of a quantum partition function, and out of that you get the quantum theory. But in this picture, which happened out of the topology first, and so hasn't been studied physically very much, you make a category out of all the different possibilities, and then you study the properties of that category as a whole, rather than summing over them all and getting a wave function. The wave function is an auxiliary entity in relation to the category, and this should inform quantum mechanical situations in a strong way, just as it informed topological situations. But that hasn't happened yet because we haven't figured out what it means physically yet. And people who are investigating it so far are not looking at it this way from the physical point of view, as far as I can tell. But that may be just the fact that I didn't look at the archive in the right way recently. It's a natural idea. And I'll stop
You were talking about Motby, and so can you conceive of the past as a simplex?
Well, it might be a simplex. You see, that's the point. If you have a combinatorial path, if the path is here to here to here to here, then it turns into a simplex. And that's one of the reasons why the homotopy type theory is using simplicial theory. If you open the book, you see they do a lot with simplicial theory, and that's one of the reasons why they have to, because of that.
And another very trivial question. Is an identity morphism an idempotent morphism?
Certainly, it composes with itself to give itself.
Yes, thanks.
Right.
No,
and if we went back to laws of form, then you could say, well, the crossing is the morphism, and the object is the void, I suppose. And then you have a little tiny category.
Oh.
And you'll notice that the other one, juxtaposition, is an extra compositional structure. So you actually want two categories talking to one another if you're going to do laws of form with categories, it seems to me. Or maybe, I don't know, I'm not happy with the fact that I don't just get a single simple category out of laws of form. But you don't whenever you have an algebra structure with more than one notion of composition.
Thank you.
Could I ask a question? Going back to, let's take, when you do D, F, and A, D, the way that you join them up here by
right.
taking them that way, is there a way of a formal definition for flipping something this way?
Oh, well, in this case, we can do it.
Well, in this case, it's symmetrical. That one is not, B is not symmetrical. If I flip B, A is symmetrical.
You're right. So how would I express that? Well, I have a mapping from the category to itself, right? Mm-hmm. And that mapping happens to take objects to objects, but it takes morphisms, objects to the same objects, but it takes morphisms to some new morphisms. And it preserves compositions, right? If I had F composed with G, and I flipped them both, then the flip of F composed with G is the flip of F composed with the flip of G. So what I'm looking at is what one would call a functor from the category to itself. Well, one considers with categories functors from one category to another, which are structure-preserving mappings from categories to categories. And of course, that was always the important point from the beginning, that you might start with one category, topological spaces maybe, and you have some way of measuring them with a group, let's say, and so you go from topological spaces to the category of groups, and such like things are always there. Then that gives rise to a pedagogical problem in teaching categories in an elementary frame, because the functors that most people use are ones that involve a bunch of mathematics. So there's a book called Conceptual Mathematics by Lemaire and
Chanuel.
Who's the other one?
Chanuel.
Chanuel and Lemaire and Chanuel. Very nice book. And they do a lot of things with categories, but they don't talk much about functors. And that way they can stay elementary. The other category books you find immediately talk about this functor and that functor and the other functor and assume you know about rings and cohomology and this and that and the other thing. It'll take a little while before somebody writes a really good elementary book on category theory that includes all its concepts, I think.
What you just said, Lou, I think brings out something very important, which I'd like to try and get across as a take-home message about category theory for this audience, and that is, I mean, a lot of people coming to category theory for the first time from the outside have this initial impression that the notion of category is some, extremely abstract, high-level, and mathematically demanding notion. It's absolutely not. The whole point, you've just made the point. The central notion, in fact, Eilenberg and McClade said this themselves at the very beginning, the key notion was that of natural transformation. Categories the notion of category was introduced very much as an ancillary notion. A category is essentially a bookkeeping device. It really is. It's an ancillary notion, it's a bookkeeping device. It's in the way that the natural transformations within the structures which naturally fall into different categories behave, that the real, sort of, the God that's in the details is in there, because that's where the math is. But the notion of category is not some super demanding high-level abstract notion, it's really a very simple bookkeeping notion.
Right.
But what it's keeping track of is essentially the way that maps transform under composition.
That's right. That's right. Yeah. And you can come into it in a lot of different directions.
Sure.
So like, if you're thinking of graphs, then you have lots of categories immediately.
Exactly. Yes. Includes very interesting ones in the case of graph theory.
Is a category a description?
Is it a description?
Is it a description?
Is a description a description?
It's a description of a description.
Is a description a description?
Well, is a description of description?
I'd say it's a high level, it's a description of the way that things transform.
What I mean is
type. No.
Of what is it a description? It can be a description of itself.
Yeah.
In computing terms, it's a type.
I mean, you take any given mathematical structure. Is it a description? Yeah, it's a description of, but it could be just itself.
Yeah. Yeah.
But
the computing metaphor doesn't work for me because that's too concrete. It's we know about types, but there's.
I mean, I'm not happy with the word description unless it's allowed to apply to itself.
Yeah. Okay.
I don't mean a simple type, I mean a very complex type, possibly.
I mean, is a graph a description? We like graphs to describe things. They describe the subway system.
That's right.
But we understand that a graph is a natural structure.
Yeah.
And I can say it's a description of a relation.
Yeah.
But is that helpful?
Yeah.
Or is it more helpful to just think that the graph is what it is?
Yeah. We maybe back to signs.
Well, if we're talking, if you had said to me, could a category be a description, I would just say yes.
Yes.
Right.
Yeah.
But isn't an object necessarily, as far as I understand category theory, I think that what is assumed as an object is already a structured thing, has some structure in it. Or,
it's something you could name.
well, that's the name.
It is, that's all the object is to begin with. Is it's a name or something that you could name.
A label?
A label. And now it could refer to something more, or it could be nothing more than a label, like 1 dot, 2 dot, 3 dot, 4 dot. They needed to have a certain amount of structure. You needed to know that there was, that 1 really was 1 dot, but 2 was a dot and then another dot in order, right? It has a certain structure, not a lot.
But you have to conceive of if they take the category of sets, there is implicitly the definition of a set. It's not just the single elements that you take into account. You can have a set with one element, but in that case...
Yeah, sets are objects that have certain kinds of properties. They have members and so on.
Yes.
But an object in a category doesn't have any properties other than it is...
of course, yes, but...
That's the difference between that and set theory. You just went to the name, went to the notion of
that's what
name.
I wanted to say, that it's not...
That's why it feels a little strange to people who have been indoctrinated, like me. You see, what about that object? What properties does it have, right? And it doesn't have any properties at all to begin with, but as soon as I start writing down some particular category, it has some properties.
Anyway, I think we're running very much into our lunch time, which is short. So we reconvene at 2:30.
Is anybody staying here or for lunch?